All right. Okay. Thank you very much, Jason, for that lovely introduction. Thank you. Hello, everyone. So, just like everybody else, I'm really sad that Mark is not here today, but I know that he would, we're both sharing this brain cognitive neuroscience and brain studies passion. So I'm sure that he would approve what I'm about to talk about today. So my presentation's title is Shifting the Focus, Cognitive Neuroscience in Learning and Teaching. So for the next 50 or so minutes, I would like to shift the focus from teaching to learning and how our brains learn. And an important aspect that's, I believe, gravely overlooked for us educators. So I would like to start with the outline. So my presentation has three main parts. First, I will talk about why we need this shift. Why is this shift important? And how we can integrate brain in teaching. And I will also talk about some key concepts about brain, about how our brains learn. I will try to keep it as simple as possible. And the second part I will talk about, because today's presentation will focus on learning, so I will talk about 7 definitions of learning. And then the third part, readjusting classroom practices with the brain in mind, with focuses on emotions, practice, and error feedback. And I will share some of my classroom practices with you today. And we will also have a little Q&A session at the end. But I also, I would like to remind you that in the afternoon, we will have a discussion time about all brain studies, including this presentation. So if you have any questions, concerns, or comments, please feel free to join in the discussion time. Okay, so let's start with the first part. So why do we need cognitive neuroscience? So today I would talk about so many different. I will refer to so many different writers and books that I've been reading for the last year and a half, or maybe 2 years. But the main one is Stanislas Dehaene's "How We Learn: Why Brains Learn Better Than Any Machine for Now" book. So I will refer to this book a lot today. Stanislas Dehaene is a French cognitive neuroscientist and an author, and he published many books on learning and consciousness and cognitive neuroscience. So I definitely recommend everybody who is interested in this field to read his books. So he said there will be no progress in education without simultaneously considering the emotional and cognitive facets of our brain. Everything that we do in the classroom, right, both as teachers and for students when they're learning, they all happen in the brain. And we need to consider how our brains function when we are teaching. And why do we need to shift this focus from teaching to learning and how our brains learn? Well, first of all, there's a lot of new evidence that shows how brains learn with the advancement of technology, like fMRI and EEG, those machines. And as educators, I believe that we need to be familiar with this data. And as we learn more about the brain, we realize that many concepts about teaching are outdated now. Like learning occurs passively through simple exposure, like a teacher teaching and students just passively listen, right? We now know that this is definitely not the best way of learning. And unfortunately, not a lot of teachers are interested in the learning part and how our brains function. And that creates a lot of gap between teaching and learning. And then we realize, oh, why all these teaching techniques that I'm using are not working. So I believe that shifting the focus is very important. So we're gonna briefly, hopefully, learn a little bit about the key concepts of the brain and how our brains work. But we need to understand a few things about the brain first. So I was lucky enough to teach language and mind classes this past semester. And I had a few students in my class, and this was an open college class, so it was for more for people who are interested in taking brain studies classes. So I asked this question. I said, so when we think about our vital organs, right, like heart or lungs or kidneys, we know now like what their biggest role is, right? When we think about our heart, yeah, our heart pumps blood and then the blood circulates around our body. Same thing about our lungs. So when I asked these questions to my students, they were very easily, they could answer the questions right away. And then I asked, so what about the brain? What's the biggest role of the brain? So first of all, there was like, some moment of like, oh, there's probably this and that. They had this thinking time, and then some of them said, oh, it's kind of like the captain of the ship, so we have, he's the leader. And then some of them say like, oh, it's, we think with our brains. I think that's the biggest thing. So actually, thinking is not the biggest role of our brain. Our brains are not there just because, oh, yeah, we need to think. No. So the biggest role of our brains is what we call, or what neuroscientists call, allostasis. This is simply our brain's budgeting ability to regulate the nutritional resources for the body and, of course, the brain itself. So our brains basically every single minute tries to see what our organs in our bodies need, what kind of energy, how much energy they need. And it just budgets all that energy that we use, that our bodies use. So, okay, so it's kind of like a captain, but how does it do it, right? How can our brains know how each of our organs in our bodies, including itself, how much energy it needs from all the nutrition that we get? So this is where prediction comes in. So our brains have this perfect predictive ability. It's like they're like prediction machines. So it's a little bit difficult to understand. So I'm going to use an analogy to explain what or how our brains do this prediction. So think about the last time you felt thirsty. So you were like, okay, I'm thirsty now. I can feel it. My mouth is dry and I just need to, drink water. So you feel this thirst and then you go grab water, right? And then you drink. And right away, your thirst is gone, right? You feel okay. Okay, now I'm okay now, continue with my life. Actually, physically, when you're dehydrated and when your organs need water, and then when you hydrate yourself, when you drink water, it takes at least 20 minutes for that water to reach to all those organs, right? So then how is it possible that we feel right away that our thirst is gone once we, drink that water? Well, that's actually because when we first feel thirsty, it's not really a physical feeling. It's actually our brains predicting that we're going to feel thirsty in the next, let's say, 20 to 30 minutes, which means our certain organs are going to require water, require hydration within 20 to 30 minutes. So our brain's giving this predictive signal, right? And this is what our brains do every single minute of the time for everything, including itself. It predicts, what type of nutritional needs, what kind of energy needs, what kind of emotional needs, what kind of physical needs, every part of our organs, and then goes on to allostasis. So allostasis and prediction are two important things that our brains do. In the language classroom, so what do they mean? So allostasis is basically, it explains how students' mental energy is spent managing stress, emotions, and learning demands. So think about students, when they're stressed, when they have some sort of physical pain or emotional struggle, their energy, their brains are going to use their energy to deal with that. They're not going to be able to listen or learn anything because the energy is spent on trying to fix the other problem. So allostasis is important in that sense. And prediction is when learning happens, when the brain's predictions are challenged or reinforced. So our brains are constantly making predictions, right? But some of those predictions are wrong, and some of those predictions are different. And when we're learning, which we will see in the next chapter of our presentation, that learning happens when those predictions are kind of challenged or reinforced or changed. Okay, so moving on to other two important key concepts. Abstraction. So abstraction is also a little bit difficult to understand, but I'm going to simplify it very, hopefully, in a very, very simple way so that everybody can understand. But abstraction basically helps us understand how the brain processes complex ideas by generalizing it across experiences. So let me give you the example, which is going to make it easier for everybody to understand. So think about the word chair, right? The moment I uttered the word, everybody probably had an image of a chair, right? Because we all know what a chair is. We know the concept of a chair. We've seen many chairs before. And we think about chair as it is. So our brain doesn't really focus on every detail of the chair that we've ever seen before. It just has this abstract representation of what a chair is. So this is what it is, right? This is what abstraction is. Our brains have this ability to have this abstract representation of concepts instead of focusing on little tiny little things like a seat or a backrest or legs in order to understand what that concept is, right? So when we see these type of different shape, different size, different color chairs, we do understand that they're all chairs. So our brains are doing abstraction, right, to understand this concept. So we do that all the time, right? Our brains do that all the time to recognize and categorize the concepts, even though they look different, they come in different shapes and sizes and colors, right? So abstraction enables students to transfer learning across context, but it also requires enough practice and variation. And we will talk about that in the next chapter. And the last thing that we need to understand is memory. So memory is kind of easy to understand because we all know what memory is. We all remember our past experiences. But why do we really have memory? It's not really just to remember things, actually. It is, when we think about it, right? It is to equip our predictive brain with models to help it navigate now. So we have memory because we need to use it now, right? Since the main function of our brain is adapting to the environment and allocating resources with allostasis, it must predict what's going to happen and budget everything accordingly, right? So predicting allows the brain to ignore most of the information that is not necessary and then keep the ones that will be useful. That's why we don't remember everything, right? And that's why when we're learning, we have, it's difficult to learn because we have certain parts, the important parts that are kept in our memory, and the rest is all gone because they're not important. So effective learning relies on encoding, making information meaningful, and frequent retrieval to strengthen the memory. So we are going to talk about how we can do this effective learning and encoding, and how can we do retrieval, right? Okay, so basically, to understand all these key concepts and to apply them in the language or in the teaching classroom. So we can say allostasis creates the conditions for learning for our students, whether they're stressed or in physical pain or in normal, perfect states where their brains keep their energy for learning. Prediction engages the brain, right? Challenges it, reinforces it, changes it. Abstraction solidifies the understanding by applying to different contexts of the same concept. And memory ensures retention. So these are just a few things that our brains use, our brain's ability when we're learning new things. So of course, we need to know all these things in order to teach better, in order for our students to understand better. So let's focus on how we can define learning and how we can define maybe teaching. So learning is a shared experience across species. Humans are not the only species that learn, right? When a baby elephant born or a baby dog or any type of babies in the different animals, they all learn how to live, right? They all learn certain things. They learn to hunt and to survive. But teaching, however, seems to be limited to us humans in a school environment, in an environment where we encourage our toddlers and our kids to go and learn things in a teaching environment, right? But this type of teaching that we do can only be extended when we align it with our cognitive skills, which we are going to focus on today. So the next chapter, I'm going to talk about how we can actually define learning, which is not that simple. But there are we're going to see 7 different definitions of learning. It doesn't mean that they're all multiple or, different kind of, oh, there's this possibility or this possibility. But actually learning is a combination of all of them. But if we have to if we can summarize, if we can sum up how learning happens or how we can define learning, according to Dehaene, of course, it could be this, right? Learning consists of forming an internal model of the world. Through learning, the raw data that strikes our senses turns into refined ideas, abstract enough to be reused in a new context, smaller scale models of reality. So I know this sounds really, really difficult. What do we mean by internal models of the world? What do we mean by raw data that we receive with our senses? What do we mean by refining them and then making them abstract enough so that we can be reused? So all of these we're going to see in the next chapter. So this is Stanislas Dehaene. I think I'm pronouncing his name right. He's French. I'm not sure. I do speak French, but not the names, apparently. So 7 definitions of learning according to Stanislas Dehaene. These are some of them are very easy to understand, and some of them are quite conceptual, but I will try to make it simple for everybody to understand. So the first one, he says, learning is adjusting the parameters of a mental model. So what are mental models? So mental models are basically everything that we see in the world, in our own world, right? If we are in Japan, if we grow up in Japan, Japanese would be the language that we see in an outside world, 99% of the time. People around us, our families and our friends, our environment where we grow up, what kind of place we live in, right? So all of these external things that we receive, we have an internal representation of that in our brains, basically. So if I see this room with a table and an air conditioner in the kitchen and a water bottle, all of these have a little internal representation in my mind. So learning is basically adjusting these little internal mental models. And how does our brain do that? So our brain searches among so many different possible settings of those internal models for those that best correspond to the state of the external world, right? So the thing about the external world is it's constantly changing. So our brains constantly need to adapt to these changes. So if we see something that we're not familiar with, our brains need to come up with a mental model right away, right? So learning is kind of like that. Our students have to change their internal models to adjust to the new external models. When it comes to languages, right, our students are coming from a Japanese language background, and when they come into the English language background, English language classroom, they are going to have this new external model, and they have to readjust. They have to change their internal models. So learning can be defined like that. The second definition would be learning is exploding a combinatorial explosion. Human brain has almost infinite number of neurons and synaptic connections that creates almost infinite number of mental models. So those mental models come with all these neurons in our brains. Of course, they're not infinite, but there's so many that we can almost call them infinite, right? But how do we understand all of these things? How can we make all these mental models? Well, the human brain makes it easy to learn and to understand by breaking it down into multi-level models, this hierarchical thing, right? So a language, a human-made concept, right? Language can be found in nature. We make languages. Language is a perfect example of that. So a language follows that kind of multi-level model, right? You have the easy part, the sounds, and then go out with words and phrases, sentences and paragraphs. So this makes it easy for our brains, for an infant's brain, for a toddler's brain to learn a language, a second language, and a third language. So our brains kind of do that a lot with new things that we learn, right? The third definition is learning is minimizing errors. Making errors is essential because it provides useful information that allows one to reduce the gap between those multi-level models. So when we are learning new things with this kind of multi-level system, if we make mistakes between each level, right? And if we kind of minimize those mistakes, our brains kind of, it's easier for our brains to learn, basically. Errors, because errors highlight that the brain thrives on trial and error, because each mistake provides feedback that refines mental models, right? So the feedback that we receive with our trial and error, that, okay, I did this and I'm not going to do it again next time, is very important, which we're going to see in the next chapter, right? So learning is minimizing errors. The fourth definition is learning is exploring the space of possibilities. So we all encourage our children to go and play, right? Playing is such an important thing. And children love playing games, playing outside, spending time with their friends. Playing is the biggest example and the most important example of an unsupervised learning. When children play games, they go into learning mode. And games are great because games add a little bit of randomness in it, right? So when, even if kids play the same game, which has rules and different, systems, and maybe they play the games with different people, there's still, every time they play it, there's still going to be a little bit of randomness. Those randomness, right, apparently is perfect for our brain. It's an essential ingredient for any type of problem. So how did neuroscientists find that information? Actually, with AI. So when they were trying to test new AI systems in the past, they realized that the AI was making mistakes multiple times because they were given limited amount of possibilities to AI when they were trying AI to answer some questions. And the AI was like in maybe the fifth time making mistakes. So they said, okay, if we add a little bit of randomness, the mistake level kind of decreases like a lot. So human brains kind of learn like that too. We need to create environments for our students when for them to kind of self-explore a little bit, okay? Too controlled environments can kill that randomness and can kind of hinder learning process. So if we give a task to our students, and if we kind of give a sample of the same task that's been done, and then we say, okay, I want you to do exactly the same thing, that is not learning, right? So we need to let our students to have this little bit of a self-exploration moment. The fifth definition is learning is optimizing a reward function. So I mentioned a little bit, but there's two types of learning, supervised and unsupervised learning. So supervised learning is, yes, what we do with in the school, for example, because we give feedback, quality, and accurate feedback. But most of the time, there is a lot of unsupervised learning happening in life when children play games. So with unsupervised learning, there's this thing called metacognition that happens to everyone, basically. So metacognition is the ability to know oneself, to self-evaluate, to mentally simulate what would happen if we acted this way or that way, so that we can know, right? So there are different parts of our brains that work as critique, right? Or that work as people that kind of cooperate with you, or that work as, oh, okay, I want to simulate what you're doing. So we have all these parts in our brains, and we kind of, they allow us, right, to foresee and imagine the results of our actions, or they kind of assess our abilities and predict the rewards or the punishments that we might get. So this metacognition is very important. And what is a brain's reward? Of course, a dopamine, right? When we get a reward, we release happy hormones. So it's very important to have metacognition abilities, which means we need to make sure our students can criticize, correct, and simulate their own actions. The sixth definition is learning is restricting search space. So we learned about abstraction, and we know what abstraction means, right? We need to have the ability to generalize certain concepts so that we can apply it to different contexts. So this works perfectly with this definition. The key to learning is the ability to generalize what is already known to new situations. So what is learned in one place can be reused everywhere else. So when we have the concept of chair, we know what a chair is. So every time we see something that looks like a chair, we understand that that's chair. And we know that the function of that is for people to kind of, use it to sit on it, right? So reducing the amount of parameters allows the brain to recognize things faster. We need to restrict the search space. So if we understand what the concept of chair is, we don't need to analyze anything else about the chair because we know already. So we need to kind of restrict that space of like, okay, now I know what that means. And if I don't need to readjust, if there's no other definition, or if there's nothing else I need to learn about chair, then I don't need to go back to that anymore. I have to like kind of restrict that space now. Okay. And the last definition is learning is projecting a prior hypothesis. So what we know now is that none of us are born with a blank slate. So babies born with this innate knowledge, right? And this is due to years and years of evolution, right? We're not like, oh, okay, we don't know anything, and the moment we're born, we're just, learning new things. Brains don't work like that. We already have priors in our brains. We already have certain evolutionary knowledge of how things work. And we are basically, we have these priors, what neuroscientists call priors. And we learn by eliminating the hypotheses that don't match with our environment. So we're all basically scientists as toddlers. Learning in man and machine always starts from a set of priori hypotheses, which are projected onto the incoming data and from which the system selects those that are best suited to the current environment. Babies are born with millions of thousands of neurons in their brains. They have more neurons than anyone that we know now as adults. But as they grow old and as they learn things, the neurons that they use, right, when they're in their brains, then those neurons get stronger, and the parts that they don't use, they just eradicated or just disappear. So these are all 7 different definitions of learning, and these are all actually a part of just one thing, and we all use all these definitions in when we learn things when we don't really realize. So the third part of my presentation is about kind of using these in a classroom environment. And I'm going to focus on three things. Of course, there's so many things that we can talk about here, but I don't have enough time. So I'm just going to focus on three things. And the first one is the importance of emotions. And by the way, I'm going to recommend more books and more authors. So the next one that I'm going to recommend is this Mary Helen Immordino Young, which actually was recommended to me by another brain sig legend, Amanda and Curtis. So Immordino Young said, it's literally neurobiologically impossible to build memories, engage complex thoughts, or make meaningful decisions without emotion. And after all, this makes sense. We only think about things we care about. So emotions are a very, very important part of a learning process and for our lives, basically. Another really famous cognitive psychologist, Lisa Feldman Barrett, wrote this book called How Emotions Are Made. So according to her, emotions are constructed. So how can we understand that? I'm going to do a little experiment, a little test to kind of understand how emotions are constructed. So I want everybody to look at this picture. Can everybody see it? Okay, so what do you see? Does anybody have an answer what this could be?
Flags.
Flags, okay. Okay, interesting. So what happens now, the moment you saw this image, right? We all have like, oh, okay, our brains are really trying hard to kind of understand what it is by retrieving past experiences, by checking all the files in our brains. We're like, okay, what is it? What is it? We're trying to make sense of this. Now, if I reveal the photo, the actual photo, okay, so now when we look back at the blurry image or this blob, it makes sense, right? It's a bee because it's something that we know and we can see that it's a bee, right? We have all these like, here and oh, okay, I can see the bee here right now. This is the. So your brain now, when you saw the actual photo, your brain added stuff from the full photo into its vast array of prior experiences because we're familiar with this photo, right? But it constructed this familiar object you now see. So emotions, according to Barrett, are like that. We are constructing emotions. All the emotions that we feel are constructed with our past experiences and with the things that we know or we learn in the past. So emotions are very important in the learning process. And how can we use emotions in the classroom? Stories, right? Having stories or sharing stories, being or feeling familiar with the examples, with the stories, with the people that we use, the student teacher and the student relationships that create certain type of emotions, and of course, creativity. So I have this example that I did in one of my classes. So I thought that I could maybe share with you guys. We don't have enough time to watch the video, but it's like a little video that you can find on YouTube. It's called Happiness by Steve Cutts. And it's basically it's like a sarcastic kind of a commentary maybe on the capitalist life. And there's like rats in the video that work, they're like, as humans, and they work really hard and they live in this capitalistic world. They try to be happy by working hard and making money. So and suspiciously they live in London. But anyways, so they basically we watch this video in the class and we have this kind of discussion session with the students. And in the video, there's no humans, there's just rats. But even with rats, we kind of analyzed the story and we realized, oh yeah, this life, the rat life that is presented in the video is actually very similar to what we experience now, right? So I asked them, after the discussion time, I asked them to kind of write their thoughts on this video. And some of my students said things like, oh, I think this film shows the reality of today's human lifestyle. This film gave me a lot to think about, the reality of happiness. And or the scene represents our blind ambitions while criticizing our lack of gratitude. So they had these like kind of deep thoughts about their own societal system and what, or maybe their future, right? So it became very, very familiar. It became very personal. And when I was reviewing that unit a couple of weeks later, I asked the students, okay, so what do you remember from this unit? Because we did so many other things. We did new vocabulary, we did new stories, we did new assignments, even presentations. And most of them just said, oh, I remember the rat video, right? So the reason they were remembering that is because they had this story and they connected emotionally to that story. The other thing is practice, right? We all know how important it is to practice. And there are different, obviously, types of practice. And today I'm going to focus on two types of practice that works perfectly with our brains. The first one is called retrieval practice, right? It can involve several cognitive activities that lead to stronger learning, retrieving knowledge, and earlier training from memory, connecting those to new experiences, and visualizing and mentally rehearsing what you might do differently next time. So this is good with abstraction and with memory. So what I do with retrieval, every time for each class, I do a retrieval practice in the beginning of the class, and I do it in halfway through the class after a 45 minutes of a 90-minute class. So the first time you do it before you start anything, you retrieve what you learned in the previous class, right? You do like a little bit of a warm-up retrieval questions like, oh, even you can start with personal things. Oh, what did you eat today? What did you do? And what did we talk about last time? And then in the halfway, you just go over certain things. So maybe we can do it together. Maybe if you want to answer, if you don't want to answer, you can just answer on your own. But let's try to answer these questions. So before we start this session, what did you have for lunch? Try to remember. What was the last book you read? What's one thing you've learned so far? Do you remember any of the brain concepts that you saw earlier? So your brain right now, even if you're not answering out loud, it's going back and retrieving all these information, all these new information that we kind of saw, that we learned. And this is important when we're learning new things, because we're getting that and we're not just putting it somewhere, right? So it's very, very important. The other one that neuroscientists recommend is called interleaved practice. So this boosts learning by mixing up closely related topics, encouraging discrimination between similarities and differences. So we are familiar with the blocking system, right? We all do this. We have topic 1, topic 2, topic 3, topic 4 within the same unit, for example. And we do topic 1 and then move on to topic 2. Okay, we review topic 1 and then move on to topic 3, review topic 2. So we kind of like have this blocked kind of system. So interleaving basically says that you can kind of introduce topic 4, for example, while simultaneously reviewing topics 1, 2, and 3. So this is good when you kind of have space in between learning things and also retrieving them all together. And this is good when it's closely related topics. Please don't confuse this with like, oh, I can just teach them new topics and then just combine them. Of course, this is not how it works, but this works because of abstraction, right? How I kind of explained the chair concept. So if we do interleaving, our brains kind of make that connection with other context about the same topic easily, right? If I learn about the chair and now I understand what a couch is, now I understand what a sofa is, now I understand how sitting works, so related things. And you can use the same concept to kind of apply it to different contexts. And the last thing is error feedback. So we did talk about minimizing errors and how important it is to minimize the errors in order to learn things. And feedback part is very important. So Dehaene said, errors always recede as long as we receive feedback that tells us how to improve. The quality and accuracy of the feedback we receive determines how quickly we learn. So it's not just, we all give feedback and we all get feedback as well in life, but it's not just the feedback that we receive, it's the quality of the feedback and it's the accuracy of the feedback that is important in learning. So he also mentions this Australian, I think he is an education specialist, yeah, called John Hattie. And John Hattie and Shirley Clark has this book called Visible Learning Feedback. So they claim that, yeah, just like Dehaene, they claim that the quality of feedback that students receive is one of the determinants of their academic success. It's a very short book. I kind of really like this 8 steps toward feedback for a learning thing that they did for effective feedback. So they say effective feedback sparks learning. This is the first step. And then it flourishes in the right environment, right? It clarifies for students where they're going. This is very important. They need to understand what the goal is, right? It informs students how they're going there. It highlights the next steps for improvement, right? It matches the needs of the learner. Of course, it promotes students' self-regulation, the metacognition that we did, right? The self-evaluation, and it flows bi-directionally between learners and teachers. So another thing about feedback is not just teachers giving feedback to students for the things that they do. It's also students giving feedback to teachers or students giving feedback to other students with each other. So all of these are kind of important. So if we have to sum it up, and it's a little bit early, but basically the whole point, the whole goal of this presentation was we need to align, right? Because when we align teaching with how the brain learns best, we unlock greater potential for every student. And I believe that we should all experiment with at least one new neuroscience-informed strategy in our teaching. Whether it be using stories, right? Using emotions in our classes, using different practices, retrieval practice or interleaved practice or spaced practice, or understanding the importance of error feedback, or understanding or giving chances for students to make mistakes and minimize their own mistakes and recognize their own mistakes and self-evaluate. And all of these things are neuroscience-informed strategies that we can use in our classrooms. So that's it from me. Thank you so much for listening. These are my references. I guess we can have a little bit of a session for Q&A if you have any questions.
I'm gonna go ahead and I'll stop the recording now if that's okay. Just if anybody wants to ask questions, I don't want them to be on the spot necessarily recorded. So I'm gonna go ahead and stop the recording there.